Good evening to those in Europe, good morning or good afternoon to those in North America, and good early morning to those in Australia. Today we will have an ammonia project feature about low carbon fossil-based ammonia in North America. So today I will talk with Blake Adair and Amgad Elgowainy. But before doing that, I want to introduce what we did last time. So next slide, please. So last month we had a similar session where I went into discussion with Jurgulf Eidesen from Horizon Energy and Toby Lockwood from the Clean Air Task Force, where we just discussed low carbon fossil-based ammonia in Europe. And one of the takeaways of that conversation was really that we want to set a standard for the industry, and not only in terms of CO2 footprint, but also in terms of other sustainability criteria, such as the actual footprint of the plant, but also water usage. So that was one of the takeaways of that session. Next slide, please. So in between these webinars, also something quite interesting happened. So we actually published our report, Innovation Outlook Renewable Ammonia, which is a report that the Ammonia Energy Association worked on with IRENA. And this collaboration resulted in this nice report of about 100 pages, in which we detailed the current status of renewable ammonia, the current markets of ammonia and the future markets, and how this might evolve into the near future. Next slide, please. And actually that brings us to today's discussion. So we are on this road to where ammonia becomes an important energy factor in the future. So it can be for power generation, it can be as a maritime fuel, it can also be decarbonized for current applications such as the fertiliser industry. And today I'm going to talk with two people about that. The first one is Mr. Blake Adair, who's the manager of projects, innovation and product development at Nutrien. So he will discuss existing plants at Nutrien which use alternative feedstocks for ammonia production. This is fossil-based, but different than a typical steam heating reforming based natural gas ammonia plants. And after that, Dr. Amgad Elgowainy, who is a senior scientist and group manager at Argonne National Lab. He will give us an overview of life cycle assessments of such alternative feedstocks for ammonia production. And with these two gentlemen afterwards, I will have a discussion in which we try to see what's kind of the landscape for low carbon fossil-based ammonia in North America. And with that, I would like to give the floor to Mr. Blake Adair. Blake, the floor is yours.
Hey, great. Thanks, Kevin, and appreciate the opportunity to come and have a great discussion today. So I've got, I'll speak for about 10 minutes and give a perspective on how Nutrien's looking at this space, and really looking forward to having some questions and comments and some discourse around this topic. And so today, I mean, just as I kick things off, a little bit about Nutrien. We're amongst the world's largest producers of fertilizer today, but also one of the largest supplier of agricultural inputs for farmers, where we have a lot of face-to-face contact with farmers just around the globe. You can advance to the next slide, please. There's just some legal disclaimer that I won't go ahead and read, so you can go to the next, please. Next slide, please. Thanks. So one of the things, and you'll notice just over my shoulder here, or this shoulder, I should say, is a lot of our strategy when it comes to the environment and ESG is centered upon UN Sustainable Development Goals. And we're in a unique position to impact zero hunger, but we also recognize that you can't necessarily solve one sustainable development goal without impacting another. And that's where we're really supportive of a systems-based approach to transform agriculture. And also, as we think about ammonia in the context of potential uses as a source of energy. And this is especially important because as we have to adapt to the adverse impacts of climate change, we need to foster climate resilience, lower greenhouse gas emissions in a manner that does not threaten food production. And I think that's something that's extremely poignant and important today, especially as we're sitting at a time right now where not only food pricing, but access to food is a real concern around the globe based upon current events. Thank you. So go to the next slide, please. So when we take a look at our overall Feeding the Future plan, we're really kind of focusing in today just to talk about a little bit about what we're doing around environment and climate action. And I'll go ahead and slip us to the next slide, please, Kevin. Thank you. And that's where we've got three main goals that are out there, and one of which is that we're supportive of the industry kind of industry-led and collaborative approach for a science-based target for industry. And in advance of that, we've committed to a 30% reduction in greenhouse gas emissions by 2030 per ton of product. We've committed to investing in new technologies, including the transition to low carbon fertilizers, including clean ammonia, and also to reduce greenhouse gas emissions in our nitrogen business unit by 1 million tons by the end of 2023. And that's where, if we jump to the next slide, really like to share how Nutrien's thinking about development of ammonia from where we are today to looking to the future. The International Energy Agency completed a report to the technology roadmap on sustainable ammonia production. And the report really highlighted that there's two primary pathways that are needed to be developed rapidly in order for us to reach a sustainable ammonia production. We need to take urgent climate action here. And in order to address just the existing ammonia production that we have today, so if we're not including increased demand from energy or as a hydrogen carrier, we would need to develop 300 megawatts of electrolyzer-based ammonia production every month, and a project that captures at least 1 million tons of CO2 every 4 months between now and 2050, just to satisfy this current demand. So it's key that both of these pathways need to be developed as quickly and responsibly as possible, and playing to the strengths of regional geography. When we look at internally at Nutrien, really coming up with what we're defining and how we look at defining clean ammonia, there's a few key important criteria. The first of which is that you're mitigating or capturing at least 90% of the CO2 emissions. Any design pathway that we're looking at, we want to have a credible way of reaching net zero emissions in the future, using technologies that are not overly expensive or difficult to implement, and to ensure that the new ammonia production we're bringing online is aligned with sustainable development scenarios and is compatible with the Paris Agreement. Now, there's still a role to play for low carbon ammonia. That's what we're amongst the world leaders in producing today. And from our conventional plants that were built kind of decades ago using older technology, we can lower the carbon footprint significantly. And that's what we do today in Redwater. We capture CO2 from our facilities and sequester it. We also do that at our Geismar, Louisiana location, and also in Joffre, Alberta, where we're able to take advantage of low carbon intensity hydrogen that's produced as a byproduct from one of our neighbors up there. Go to the next slide. So I guess kind of focusing in on some of the potential pathways, the fossil-based pathways to start with, would be for low carbon ammonia would be a conventional plant. So in a conventional plant, in relatively simple terms, you've got two primary sources of emissions of greenhouse gases. The first of which is in the primary reformer. That's where we're taking our feedstock of natural gas and steam, and we're converting that over into syngas. So that's where we're getting our hydrogen and our CO that will eventually be converted to CO2 and captured. So in a conventional plant, somewhere between 30–40% of the emissions come from just combustion of natural gas. This reaction requires a lot of energy. You get that energy from burning natural gas, and these combustion emissions are relatively low in concentration of CO2, which makes them very expensive to capture, not only from the capital equipment required, the land and the footprint to put these large capture equipment, but also the ongoing utilities in order to run them. The other primary source of CO2 from an ammonia facility is what we call process CO2. So that's all of the carbon that's in your natural gas feedstock that eventually is converted from methane into carbon monoxide, into carbon dioxide, and captured. Now, the CO2 from these plants around the world today, they can be used to make urea, which is a very important and common agricultural product. They can be directed towards sequestration, And as I indicated, this is exactly what we're doing today in our Redwater, Alberta, and Geismar, Louisiana facilities. And in a lot of cases, the CO2 is vented today. And so that's where there's I guess, a low-hanging fruit of any process CO2 that's being vented, looking for opportunities for any sort of geologic sequestration or minimum utilization in some way, shape, or form. Next slide, please. So there is opportunities within a conventional design to lower that carbon footprint. It's possible, especially if you're designing a new plant, that you can increase the amount of processed CO2 and decrease the amount of combustion emissions, and also perhaps oversize that front part of the plant where you're making the hydrogen and recycling some of that hydrogen back to displace some of the natural gas that's burned in the primary reformer. However, to get to a net zero design where you're really avoiding any sort of fossil fuel combustion on site, you're still probably going to need flue gas capture again, which is kind of a challenging option from an execution perspective. Next slide, please. And then lastly, the technology that we're most interested in Nutrien when we're looking at building a new plant is autothermal reforming. And the nice aspect of autothermal reforming is that almost all of your combustion, your steam methane reforming, everything is, as I like to say, happening in the pipe. So it's really easier to capture higher levels of CO2. And so within these designs, you can capture greater than 90% of the CO2 overall using the reaction. You also have the ability to oversize your front end, and instead of burning natural gas as a fuel, you can just consume hydrogen, making for the design of the plant as close to net zero as possible, as you have no direct natural gas fuel combustion overall. When this is paired with secure geologic sequestration, you can achieve, like we said, at least 90%, if not higher, greenhouse gas reductions. And this is something that can be done at scale today. And I won't go into too much detail, but just last week we announced our intention to build a facility of this utilizing this technology that could be up and running as early as 2027. So really, we're obviously at Nutrien very excited about this development of this technology and look forward to having some more discussion. Next slide, please. Now, I know this was going to be focused a little bit more on fossil, but we need to also consider the other pathway, which is using electricity produced with a really low or even zero carbon footprint in order to make the ammonia. Of course, we can use wind, solar, nuclear, hydro, all of those options, and then combining those with water and electrolysis and air separation units to get nitrogen from the air to make ammonia. And the key part here is this is very sensitive to the carbon intensity of electricity that we're utilizing, whether it's off-grid or on-grid, as well as sensitive to price as well. There's a significant amount of electricity required for ton of ammonia. Next slide, please. And with that, really high level, looking forward to the questions, and you can click the link here if you want to learn a little bit more about what we're hoping to do with our Geismar facility. Thank you.
Thank you, Blake, for the very, very clear explanation of the different pathways. I think it's really nice that you showed that we go from current SMR, steam methane reforming based plants where you have low concentrations of CO2 from the off gas to ATR, autothermal reforming based solutions, which can actually capture the CO2 at a much lower cost. And then you also touched upon the renewable ammonia landscape. And now I really want to give the floor to Dr. Amgad Elgowainy, who really puts this into perspective from a carbon intensity perspective. So Amgad, the floor is yours.
Thank you, Kevin, and thank you, Blake. Can you start my slide? Thank you. So what I will show you today is a work we have done with support from the US Department of Energy, the ARPA-E program, where we were looking at pathways for low carbon ammonia production, including actually a baseline conventional ammonia production, looking at the life cycle analysis, looking at also the techno-economic analysis. So I want to take you through that study. First, I would like to acknowledge my colleagues, Kayuha Lee, who is also a first author on a paper that is forthcoming in Green Chemistry, which will have a lot of the details of what you will see today, Senulio, Pradeep, and also Ping San. Next slide, please. So our scope there is to start with a process level modeling. What you see on the top left is a blue box. I mean, basically, this is important for us to understand what equipment is needed, size the equipment, understand the material energy balance, the product yield per unit of input, utilities, everything, and then run a techno-economic model accounting for all of these, and then circle back, optimize the process, and come back to do the techno-economics. Also, we need the material energy balance to feed into the life cycle analysis model. This is the Argonne grid model that does life cycle analysis for ammonia and other products and fuels, and then pair the two to say for a certain technology pathway to produce ammonia. How much does it cost to produce the ammonia, the levelized cost, and then how much emission life cycle associated with the production, also per unit of ammonia produced, and then compare these to the conventional ammonia pathway using the current cost and the current emission of the conventional pathway, and then do delta cost over delta emissions, and kind unifying the techno-economics with the life cycle analysis into one metric. In this case, it will be cost of avoided CO2. Next slide, please. So this is starting with the pathways we look at. So on the very top, block number A, actually, this is a conventional pathway, similar to what you have seen in Blake's slide. So you rely on natural gas as a feed, you use a reformer, and then a water gas shift, then you will have some CO2 removal, followed by methanation, and then you supply the hydrogen and the nitrogen to a Haber-Bosch to produce the ammonia. You can do the same, and they capture the CO2. As Blake mentioned, there is CO2 from process, there is CO2 from the flue gas, I mean from combustion, and you have opportunity to capture the process only or the process plus the CO2 and flue gas. These two cases will give you different carbon reduction and also different costs. So this is block number B. And then lastly, what Blake showed in his last slide, the potential to use power. I mean, basically to split water, use power for air separation, get the nitrogen, and then feed the hydrogen and the nitrogen to a Haber-Bosch to produce the ammonia. And in that case, your ammonia carbon footprint will depend strongly on the carbon intensity of the power used to produce the hydrogen, and to a smaller extent in the power used to produce the nitrogen. Next slide, please. So this is what I mentioned. Process level modeling is key, actually, to tie with the techno-economics and also to feed the techno-economics and to feed into the life cycle analysis model. So this will be the different processes you see on the top through the methanation process, and then at the bottom, this is really the Haber-Bosch. Again, what is important there is to size the equipment, get the cost, the capital, understand material energy balance, get the utility cost, and then produce a levelized cost of hydrogen, of ammonia production, as well as the carbon intensity for that ammonia well to plant gate. Next slide, please. So this is the output of a techno-economic model. So based on the process level model, we feed the techno-economic models, the equipment, the utilities, everything. And there you see several pathways. You see on the far left, this is the conventional natural gas-based ammonia. And based on the modeling, based on the cost of natural gas, I believe in that case, the baseline was slightly over $4 per million BTUs. I believe it was 4.24 or something. I mean, you get roughly, if you multiply 1,000, this will be per metric ton. So it will be $229 or $230 per metric ton of ammonia. Now, I mentioned two opportunities to capture the CO2. If you capture only from the process, and this is the easiest low-hanging fruit for capture, then your costs will rise to $13. If you consider a 45Q tax credit, for those not in the US, this is really a tax credit provided. I mean, if you capture the CO2, and if you store it, you get $50. If you utilize it, I mean, for let us say enhanced oil recovery or something, you get $35 per metric ton. So you see that credit can bring the 313 down to the 250 ballpark. Now, if you capture further from the flue gases, then your costs will go up, but of course your carbon reduction will go, I mean, up as well, and we'll see that in the next slide. So here the costs will go up with and without the 45Q credits, you will be in the ballpark of 370 or 290 per metric ton. And then the last set of bars are looking at the renewable pathway, basically using power to split water to get the hydrogen, which is our energy feedstock in that case, and then the power also for air separation. And you see the 4 bars shows the cost sensitivity to the hydrogen cost. So from 483 per kilogram, and this is based on a specific reference from a US Department of Energy record for low temperature electrolysis, LTE, or high temperature electrolysis, HTE. I mean, you see the different costs there, and you see the dominant cost there is the hydrogen feedstock. This is the green portion of the bar. If you are able to hit the near-term DOE target of $2 a kilogram, then you are at $475 per ton of ammonia. If you hit the longer-term target, the hydrogen earth shot, $1 per 1 kilogram in 1 decade, then you are back to $270, not far away from the conventional ammonia produced. So you see, actually, the techno-economics can give us some enlightenment about where are the cost drivers. And no surprising there is that the cost of the natural gas feed or the cost of the hydrogen, these are the energy feedstock, are dominant. You see from the far right group that each kilogram of hydrogen contributes about $200 per ton of ammonia. So if you go $2 and this contribute 400 plus the capital, the capex, and the others, then you actually, the 400 will be 475 or the 200 will be 270. So you'll be able to see what are the major cost drivers and what, I mean, feedstock costs can contribute to the value proposition. Next slide, please. Then we look at the life cycle well to plant to get greenhouse gas emissions for the same cases you have seen in the previous slides. So you see the conventional one, you are roughly emitting 2.6 tons of CO2 equivalent per ton of ammonia. This is conventional life cycle. And then with carbon capture from the process, you are down to 1.1. And then if you capture from the flue gas, you can go down to close to 0.8 tons. And then if you go completely renewable or nuclear, you are virtually eliminating the entire CO2 from the supply chain all the way to the ammonia product. Next slide, please. And then to tie the two, the techno-economics with the life cycle, we say, where is the low-hanging fruit? What will be the cost of avoided carbon? And we look at some sensitivities. The sensitivity could be on how much carbon is captured, for example, the CO2 transportation distance, the hydrogen cost, the natural gas feedstock cost, and so these are the error bars. But you see, actually, you could be anywhere from less than 100, I mean, all the way to $300 really for certain cases, depending on, again, the major cost driver in this case will be the hydrogen from the electrolysis pathways. So with that, I would like to conclude with the next slide, just to acknowledge our sponsors, the US Department of Energy, in particular the ARPA-E program. And the next slide will just show my email and link to our website where you would see more on our models and publications. Thank you.
Thank you, Amgad. That was very clarifying regarding the carbon intensity and how these different scenarios will pan out in the end. So I got a question from the audience regarding the session, whether it will be recorded or the slides will be available. Yes, the session will be recorded. The slides will be available on the website of the Ammonia Energy Association, so ammoniaenergy.org, and recording can be viewed later via YouTube, so it will be available probably by tomorrow night. So right now I would like to go into the discussion with Amgad and also with Blake to discuss the different topics that they addressed. So first of all, I would like to go a bit deeper into the different sustainability criteria. And first I would like to ask Amgad a question regarding that. So there's very much focus on CO2 emissions, but what are very important key sustainability criteria, especially in the ammonia/hydrogen production landscape, so to say? For instance, water usage or something else. Is there anything very key here that
Okay, so the question is, if I understood correctly, if there are other sustainability criteria outside the CO2, is that right? Yes.
exactly?
So, for example, water resources, if you go the electrolysis pathway, actually, even the conventional pathway, you need water for steam and for reformation, and the others, you need water for cooling, of course. So we look at the water, I mean, especially in the US, where are the water resources, how much is available, what if you deploy a large scale program for energy, in this case, it will be an ammonia carrier. What does it mean? So this is an important. The other important matrices for us is air pollution in general, and where air pollution happens, and the implication of that air emissions on issues related to human health, environmental justice, among others. So all of these are other sustainability metrics, of course. Resource availability, how much natural gas or renewables or nuclear, and where, actually, just to get a sense of longer term, are these sustainable feedstocks, are they domestic, are they secure, and for CO2 capture and the storage, what are available storage sites? I mean, how much you can capture and store, what is the life of that storage, actually. So all of these are other sustainability metrics that will be important for these pathways that you have seen to materialize, or for other potential co-benefits from certain pathways that can be aggregated on top of the CO2 reduction.
Thank you so much. So actually, I want to move on to Blake. So you mentioned you have a few plants running on ethane cracker-derived hydrogen. Is there any way you can bank that right now to a certain application, or is this not yet in place? So what's the status of that?
Maybe I don't fully understand the question, but yeah, our Joffrey facility has been in operation for many years. So that's where we kind of think about from a Nutrien perspective. We've been a leader in low carbon ammonia before there was any kind of new markets, where we've been, the Redwater project was in development that took a decade to develop. We've been active in Geismar for almost over a decade, and Joffrey, of course, has been in operation for a long time. So that we're kind of building upon that and looking at in the development of new ammonia with these different pathways.
All right, thank you for that. And you also mentioned quite some other potential projects based on an ATR technology in the future, where you could capture most of the CO2. However, if you look at the emissions from an ammonia plant, you have, of course, scope 1, scope 2, but then also there's the scope 3 emissions, for instance, the methane leakages from your natural gas extraction. So how do you account for that within this kind of technologies?
Yeah, no, it's absolutely a very good point, and you're right on in that when we look at the life cycle emissions for the facilities, and Amgad's presentation did a great job of highlighting that. You've got your scope 3 emissions from your natural gas production, of course, and when we start to get into these kind of called the next generation ammonia technologies, especially using the fossil-based feedstock, that's going to be your primary driver for your emissions overall. You're going to be using a small amount of electricity. Although if we look at over the lifetime of these plants, at the outset, you'll have opportunities to reduce your scope 2 emissions from electricity by either generating it yourself or exploring renewable options, or just taking into account the fact that the grids, electricity grids over time are going to be reducing and getting closer to closer to net zero. And then, of course, the on-site emissions, we're essentially capturing essentially all of those at the outset, and if not all of it right away, with the design able to convert over to capturing almost everything on site easily in the future. And then, yeah, that's the upstream emissions associated with the feedstock. I think you're going to see a lot of improvement in this area over time. You know, at the most recent COP26, there's a lot of focus on reducing methane reduction. There's a lot of projects that are going to have open access to be able to see methane leaks in real time. And, you know, you're seeing emergence of, you know, not only biomethane, but also responsible natural gas, that you're actually having companies taking a very close look at the carbon footprint of how they're developing these resources, which will all translate through to lowering the carbon intensity of any derivative products from natural gas, not just ammonia.
Thank you for that. So Amgad, can you also comment on that? So how relevant are Scope 3 emissions from natural gas, so methane leakages, for the overall carbon footprint? Is this a single value that's very similar for different locations, or is there a wide range of values? So can you comment on that?
Yes, you are right. Thank you, Kevin, for the question. This is an important question. So the upstream for conventional ammonia today, with or without really carbon capture, is mainly in the carbon intensity of the natural gas supply chain. So there you have the key driver is the methane emissions, but of course there are activities in recovery, there are activities in processing, separating the natural gas pipeline quality. There is the compression station to drive the natural gas in pipelines all the way to the ammonia plant. So all of these are contributors, but you have seen in my slide, even capturing the process and the CO2 from process, CO2 from flue gas. I believe we capture 95% from process and the 90% from flue gas. You are still, I believe the number was 0.77, or I mean, tons of CO2 per ton of ammonia, which is still significant. It is not zero. So we go from 2.6 down to 0.8 or something. It is a significant reduction, but it is not virtually zero. And this is all is the contribution of the upstream natural gas. A small percentage there is for the power used, but predominantly it is the natural gas supply chain. The natural gas supply chain is very different depending on the field where you recover. Some of these have very large emissions, sometimes large infrequent emissions. Other fields are very tight in methane leakage. The transportation distance I mentioned again is a factor. So some of these actually will play into that Scope 3 emissions. And usually you go actually with some average numbers, but for each single plant, it might have a unique upstream Scope 3 emission associated with the gas plant. And I know you mentioned earlier the steam cracking plants. There is in the Gulf, of course, in the US that produces hydrogen. Some of that actually is used for ammonia. This could be slightly lower carbon than natural gas. I mean, depending on the how you treat the hydrogen byproduct from the steam cracking plants.
Thank you so much. So indeed, also for the ethane cracking plant, it's also very much related to how you allocate the carbon emissions. Do you do it on weight basis? Do you do it on energy basis? So there's quite some ambiguity there, and that's also a reason that at the Ammonia Energy Association, we are developing a certification scheme for low carbon ammonia produced. And the reason to do that is really to get a clear, transparent methodology to be able to globally harmonize the trade of low carbon ammonia, so that we can all agree on what does it mean to have a certain carbon footprint for ammonia. And now I actually want to move on for a question to Blake, a question by Daryl Jones. To what extent do the carbon tax credits available for carbon capture impact the project economics of fossil-based low carbon ammonia?
Yeah, thanks for the question. I think, you know, without going into too much detail, and if maybe folks aren't familiar, you know, 45Q tax credit will give $50 per ton over a 12-year period for CO2 that's directed to permanent and dedicated, Class 6 sequestration wells, and it'll give $35 to any sort of CO2 that's directed towards enhanced oil recovery. So if you're looking at overall for perhaps, for example, the project in Geismar that we're considering, there's a measurable impact, right, that you're going to see from the tax credit of that, without any sort of carbon tax in place or otherwise, there is a driver there on the economics for sure.
Thank you so much. So looking a little bit at the different side of the emissions. So we mostly look at CO2 emissions, but of course you're also a fertilizer producer. So that can mean that you also have nitrogen oxide emissions from downstream processes. So what do you do to minimize actually these kind of emissions? So NOxes, N2O emissions from your plants.
Okay, you're really going to test me on the flex of knowledge here. So that's so that would be the scope 3 emissions from nitrogen use, and for sure this is an area that when you look at over the entire life cycle from the well right through to use, there can be significant emissions. And so for folks not maybe familiar with that on the call, when you apply nitrogen-based fertilizers in the soil, there's a certain percentage that is going to be converted over into nitrous oxide N2O, which is a very potent greenhouse gas. And so, if I draw back to the IEA's report on sustainable ammonia development, there's an entire section on here that's dedicated to this. And there's a few pillars here, and one of the pillars that is important is nitrogen use efficiency. So, of the nitrogen that's applied for any crops around the world, maximizing the amount of that nitrogen that is available for the plant when the plant needs it, to ensure that a majority or as much as possible ends up in the plant and doesn't end up in not only converting to N2O in the atmosphere, but also in surface runoff or groundwater or otherwise. And that's probably another topic for another webinar, but that's something that Nutrien, of course, we're focused on. We've got a carbon program which we're trying to incentivize on-farm decisions that minimizes the carbon intensity of farming and tries to incentivize farmers in order to do that.
Thank you so much, Blake. Indeed, this is a very important topic because mostly we look at the production side, but especially on the application side, there's a lot to gain in terms of efficiency. For instance, if it's wet weather, you don't want to use your fertilizer right then. You probably want to wait until you get dry weather because you get a lot less emissions then. So this is something to consider. Actually, I want to move a little bit to economics, and this is a question for Amgad. So I got a question from the audience regarding the $1 per kilogram of hydrogen price. So for what kind of size of the project would you need to reach this 1 kilogram of hydrogen in a long-term scenario? So is this actually more like a target, or is this also based on a scenario that you would expect?
Yes, the $1 per 1 kilogram in 1 decade is a target. This is announced by the Secretary of the Department of Energy, a few months ago. This is the hydrogen artifact goal. How to achieve the $1 per 1 kilogram will require economies of scale to ramp up scale of electrolyzers. You would need to work with high efficiency electrolyzers. The less power you use to produce the hydrogen, the better. And of course, it will be strongly dependent on the power of the low carbon or zero carbon electricity. So all of these will have to come to play to realize the $1 per 1 kilogram.
Thank you for that. So we see a decrease in renewable hydrogen production price, and ergo also reduction in the renewable ammonia production price. So that's really on the carrot side, that we maybe also, to incentivize this kind of renewable hydrogen production, we get some tax credits. On the other side, there's also carbon taxation happening, for instance, in Europe. So to achieve like low carbon hydrogen in the future, what kind of mechanisms are very important? Is it either or is it both the carrot and stick approach? Maybe to clarify a little bit. So on the carrot side, we have the carbon, the tax credits, and on the stick side, we have the taxation on the emission from fossil-based ammonia. So what do you see as the major drivers to decrease the cost of this hydrogen, renewable hydrogen?
Is this a question for me or for Blake?
For you, and maybe Blake can follow up.
Okay.
After that.
Okay, so I mean, anything that can value, I mean, the low carbon product, whether ammonia or otherwise, will always help, right? So you have some benefit there. Why there is goals to reduce carbon emission, because it has really a harmful impact. So if you reduce that, you get some social benefit. How to value that is really the key. And it could be any of the above, actually. So in my mind, actually, and you have seen really, like we showed in our slide, existing policies like the 45Q, what does it mean, right? If you capture this much or that much, what is the implication on the cost, but also what is the implication on greenhouse gas emissions? So this is really kind of will be variable depending on where you are and how to value the low carbon product, whether hydrogen or ammonia or otherwise, will definitely be a key enabler.
Thank you. So Blake, can you also comment what has been very important so far?
Yeah, I think your question was kind of in the context of more of electrolytic hydrogen, right? And so if you look at the landscape, and if we just focus on the US right now, we have the 45Q tax credit. That's for one pathway that needs to be developed, which is great, but you're missing something on the renewable hydrogen side. And I know there was some 45X, so that's the clean hydrogen production tax credit that was contemplated as part of the Build Back Better bill, which is currently kind of has not been passed. So I think, yeah, you definitely need to see some form of incentive for the electrolytic hydrogen, and especially if you think about this from a technology readiness level, right? If you look at a large plant like 1 million+ tons of ammonia per year, there's technology that exists that, as long as you have the capital and all the other things in a row, you can execute on a project like that in a matter of several years. Where if you contemplate trying to make an ammonia plant of 1 million tons per day based upon electrolytic hydrogen, not necessarily that all of the technology and the supply chain and everything is as mature. So having some form of support for those first movers in the space will be important to kickstart it. Not too dissimilar for how solar and wind and so on and so forth were brought forward.
Thank you very much for that. So indeed, that's very much true, because if you look at a 1 million ton ammonia plant per annum, so far there has been no renewable ammonia plant with this capacity. Plans have been announced, so there are tens of projects. I believe right now about 70 projects announced regarding renewable ammonia production. But what you really see is that from 2025, 2026, maybe you see these kind of megaton ammonia plants. But up till then, it's really scaling up to this capacity. And right now, the biggest plants have a capacity maybe 10 kiloton per year, and not much bigger than that. So staying a little bit on the economic side. So I got a question regarding whether there is an economic driver for low carbon ammonia production, even in the absence of a CO2 price. So Blake, can you comment on that?
I think it remains to be seen if there's going to be a premium driven. Of course, you've got different jurisdictions around the world. Europe, obviously, the ETS there, and for agricultural products, they are contemplating a carbon border adjustment. So there's potentially a value driver there for producers around the world to reduce their carbon intensity. In the U.S., we've already kind of touched on the 45Q tax credit, and then up in Canada, a pretty substantial carbon tax there, where you can potentially take advantage of, and signals there is that could be going up by $15 Canadian per year, up to a maximum of 170 over a period of years. So I think those are some of the drivers as they exist today for
So also staying with you, Blake. So I got a question also from the audience. If Nutrien could purchase affordable, reliable green hydrogen at the gigawatt scale, would you then build a green fertilizer plant in the US?
Oh, I mean, a great question. And I think, I lean back to the presentation I gave earlier. Part of our Feeding the Future plan is to develop clean ammonia through multiple pathways. And if there's commercially viable ways that we could produce ammonia in this manner, it's certainly something we would look at and evaluate.
All right. So maybe a related question to that. So if you have green hydrogen, if you make fertilizers, for instance, if you make urea, how does this match up? So you need to get your CO2 as well, right? So yeah, how do you see that landscape evolve?
Yeah, touching a lot of topics here, but it's a real challenge for the industry for sure, right? So ammonia is the building block or the basic building block for all nitrogenous fertilizers. However, a very small percentage of ammonia that's produced globally worldwide is actually applied directly. And that's where actually for the US and Canada, those are one of the rare places that you could actually incentivize direct ammonia application in some way, shape, or form, ensuring that there's some way that the farmer gets a price signal that this is they're going to get either more income for their crop or something. There's an opportunity. I mean, there's a very large pipeline that runs right into the heartland of production there in the U.S. Your other routes are, of course, around ammonium nitrate and ammonium nitrate-based fertilizers. You don't require any CO2 in order to produce those. However, there's kind of the safety and security concerns around ammonium nitrate that you kind of have to contend with, which is dealt with differently around the globe. And then, as you mentioned, of course, urea. That's a challenge, right? If you're driving to like true, completely net zero fertilizer using completely carbon-free ammonia, you've either got to come up with another source of CO2 to make urea, or transition. You've got to transition your how you're getting your nitrogen from your plant into the soil, and that's where when I think about the agriculture industry, we're very from our decarbonization perspective, very similar to cement or steel, of a hard to abate emissions intense industry. However, at the end of the day, if you abate the CO2 from making cement or steel, you're making cement and steel. Your supply chain and how it gets to the customer doesn't have to change. If we want to completely switch 100% over to having carbon-free ammonia, everything has to change from the plant right through the supply chain to the farm, to the equipment, the storage, everything. So it's a significant challenge, and that's where I refer back to what I spoke to earlier. We're supportive of a systems-based approach for tackling this challenge in the agriculture industry.
Thank you so much. So maybe Amgad, can you also comment on that? Are there any pathways to couple sectors to get the CO2 from somewhere else for the urea or alternative feedstocks with a lower carbon footprint?
So I agree with Blake. So this will require like several approaches to minimize the reliance on CO2 sources for urea. However, in the US, for example, one major source of CO2 that is of biogenic origin is the CO2 from ethanol plants, the fermentation process. So these are high concentrated CO2 that potentially can be paired with the ammonia to produce urea. And in that case, you do not rely on a fossil source for CO2. But there are trade-offs between several of these, whether you source the CO2, whether you change a practice like Blake mentioned, I mean, downstream activities, how you apply these. In my mind also, ammonia goes beyond the fertilizers. It is a potential energy carrier that is being thought of for energy applications. I mean, whether it is for marine applications or for sometimes, I mean, there is a talk about power production. So in these cases, you don't need the CO2, but in the case of the urea, yes, definitely you would need a CO2 source, and there are few options there.
Thank you, and you're very right. So the current market, which is about 183 megatons of ammonia, is probably not the biggest market in the future, because on the energy side, you see a lot of developments. It might even be that the total ammonia market by 2050 is about almost 700 megatons, which is a huge number, of course. Now I actually want to go a bit more into the more global overall picture of the developments you've seen over the past few years. So Amgad, if you look at the past 5, maybe 10 years, what kind of change in the narrative do you see regarding this low carbon hydrogen production?
So hydrogen production has been predominantly in the US, steam methane reforming using natural gas supply. I mentioned there is quite some hydrogen now, especially in the Gulf, from the NGL cracking plants to produce the ethylene petrochemical like feedstock. There is few very low carbon hydrogen from the chloroalkali plants. These are smaller scale though, but these are again like some low carbon hydrogen. The recent activities and announcements in the US that incentivized what is called the blue hydrogen, we don't like the color, let us call it SMR plus CCS, or I mean the electrolytic pathway using low carbon electricity. All of these signifies the desire to lower the carbon footprint of the hydrogen and its application. In this case, it could be ammonia, but even other applications that rely on hydrogen. And again, hydrogen today is in refining, in ammonia production. But again, similar to ammonia, it is a zero carbon energy carrier that can play a major role in decarbonization across sectors, whether it is for longer-term storage to enable renewables or for other applications, including e-fuels, synthetic fuels, synthetic chemicals, even blending with natural gas or replacing natural gas for like residential or commercial or industrial applications. So, I mean, we see the push there to incentivize the low carbon hydrogen production and with major attention both from government and industry to ramp up the low carbon pathways for hydrogen.
And thank you. So Blake, what kind of changes in the industry have you seen over the past few years? Let's say starting from the end of the 2010s up till now.
I mean, I think I characterize this as transformational change. I think specifically within our industry, there's been heightened focus on some of the topics we covered today, which is looking at our emissions footprint across the entire value chain, right from our feedstock right through to use, and that's where, you know, from Nutrien's perspective, we are trying to make meaningful and impactful investments in not only projects but programs in order to try to address these spanning the entire agricultural value chain. And, you know, specifically on ammonia's potential role beyond its traditional use is really interesting and exciting in that it really is complementary to hydrogen, in that it can reach industries and uses that hydrogen maybe can't as effectively, and specifically around maritime shipping, as around the potential for the displacing coal, which is interesting, and then as Amgad mentioned there, you know, potentially as a hydrogen carrier, where we can leverage the existing ammonia trade and technology and everything that exists currently today of around 20 million tons of ammonia traded annually around the globe. B2C, you can leverage that infrastructure as well. So, you know, really interesting and exciting, and you know, especially I think when we look at it from our perspective, of course, we also want to see the benefits translate through to traditional uses of ammonia and decarbonization of those industries too.
Thank you so much, Blake. So just to finish off also this discussion, which has been very interesting, and as you already mentioned, Blake, we've gone into very different angles throughout the conversation. So we touched upon a lot of subjects. So let's say we are 5 years from now. What would be your ideal situation if you sketch it from a high level? What has happened?
Well, I'll go 5 years from now. Would be I'd be very happy. I'd be just finishing up or getting close to the ribbon cutting ceremony when our new plant is up and operational. And I'd love to see our Nutrien's goal to have an ammonia fueled vessel in operation as early as 2025. So we would have amongst the world's largest clean ammonia plants operational with the lowest carbon intensity around the globe, and also have starting to solve some of these other hard to abate sectors. And I guess the other piece I'd love to see is potentially within Nutrien, but also amongst around the globe, to see the other technology pathway really scale. I'd love to see larger scale electrolysis projects beyond, the 20 megawatt or the 80 megawatt, but getting into the hundreds or even potentially thousands of megawatt size projects, and seeing shovels in the ground and seeing ammonia being produced along those pathways too, because we need both in order to get there.
Thank you so much. So that's very enlightening, because it's a very positive outlook on the future. So Amgad, do you also have an idea when in 5 years it has been a great success from your side?
Well, for us as a national lab, we are supporting the government, and also through the government supporting the industry to realize their targets for carbon reduction, whether for ammonia or hydrogen or others. And we have seen like the US government did enact a bill recently incentivizing low carbon hydrogen. I believe $8 billion are there, $1 billion for electrolyzers, another $500 million for manufacturing, recycling. So you see really the government is keen really to push. There are other programs, for example, the direct air capture, and so I did mention that this could be an opportunity if you want to make urea. Actually, this could be like a way to also provide a source. Of course, all of this will depend on the economics. Our goal is to make these goals and the pathways to these goals successful by supporting both the government programs and the industry deployment plans.
And thank you so much for that, Amgad. So actually, we are almost finished with the hour. So I want to thank both of you for the very fruitful conversation we've had. Just as a reminder for all the participants, the session is recorded. So actually, the recording will be online on YouTube probably by tomorrow night. The slides will also be available on the website of the Ammonia Energy Association. And actually, because this is a series of webinars, next month we will have another webinar. So toward the end of June, we will discuss low carbon fertilizers in Europe. So we will do that together with Yara and with Fertilizers Europe. More details are to come. And with that, I want to thank you all for listening from all around the world. And I especially want to thank Amgad and Blake for hanging on with me for 1 hour in the discussion. Thank you so much.
Thank you.